Hello everyone, my name is Tiffany Roberts and this is my Lab 4 Oscillations presentation. In this lab, we are analyzing the motion of a mass oscillating on a spring that is attached to a fixed point using tracker. We assume the mass of the spring is negligible and the fixed anchor point does not do work on the system. We are defining the system to consist of the mass, spring, and earth. We use Newton's second law and the energy principle to predict the motion and energies involved. Finally, using GlowScript, we will create a computational model of our system using data from tracker and compare the two in our discussion. In tracker, I set the origin to be the fixed attachment point with a negative y direction pointing straight down. After going through each frame and plotting the points of mass in the system, I copied the x and y position data over to a CSV file to later be used within the GlowScript code. In order to define the period, or t, of the mass's oscillation, I chose 2 points as highlighted as an initial and final time in order to calculate an average. Over these 3 periods of oscillation, I found t to be equal to 1.646 seconds. I then will use t to solve for the stiffness of the spring. Since we know t is equal to 2 pi times the square root of the mass divided by the spring stiffness, we can rearrange the equation to solve for k. In this case, it's 4 pi squared times the mass divided by t squared, and I found it to be 5.858 newtons per meters. Now we can solve for our relaxed length, L naught, using the spring stiffness. As shown by the equation, the magnitude of the force of gravity is equal to the magnitude of the force of the spring. Therefore, mass times gravity is equal to the spring stiffness times the stretched length, minus the relaxed length. We can rearrange this equation to be L naught equal to the stretched length minus mass times gravity divided by the spring stiffness. I found the relaxed length of the spring to be equal to 0.0274 meters. Moving on to my GlowScript code, I set my initial conditions including the mass, which is 0.402 kilograms, the initial position of the mass, found using tracker, which is a vector negative 0.11, negative 0.6330, and the initial velocity, which starts from rest, making it 0 meters per second, and the initial time, which is 0 seconds. Our other initializations include the gravitational constant, the spring stiffness, and the relaxed length of the spring, both of which I calculated previously. As stated before, we set the system to include the mass, the spring, and the earth. There is no external work done on the system. Therefore, the kinetic energy is equal to 1/2 mv squared. The gravitational potential energy is equal to the mass times gravity times the y position of the ball, and the spring's potential energy is equal to 1/2 times the spring stiffness times the square of the stretch. At each step, while t is less than 9.212 seconds, the energies are updated using the energy principle, and the position and velocities are updated using Newton's second law. Using the energy principle, we determine the total energy to be equal to the sum of all the energies, and the change in the total energy to be equal to the sum of the changes of all the energies. Running the code, I must upload the CSV file as I mentioned earlier in the presentation, in order to import the position data from tracker into GlowScript. We see the blue dot representing the computational model and the red dot representing the motion analysis from tracker have similar but not quite identical paths. In the y position versus time graph displayed, the blue represents the computational model and the red represents the motion analysis from tracker. The main trend we see is that the experimental results begin to have a shorter period and decreased amplitude as time increases. This leads to 2 possible conclusions. One, that the experimental system is losing energy due to friction, or that since this is only the motion in the y direction, that simply more motion is being translated into the x direction rather than the y. So going into some what does it mean questions. As stated previously, our system is defined to include the mass, the spring, and the earth. There is no work done on the system by the surroundings, which means there is no change in the total energy, meaning the total change in energy must be equal to 0. In the graph shown, the total change in energy is represented by the yellow line, which satisfies the energy principle. Comparing tracker's x and y oscillation periods, the values are close but have a noticeable difference where the x direction oscillates approximately 0.1 seconds slower, most likely due to the initial position input being more dominantly in the y direction. This concludes my Lab 4 presentation. Thank you so much for watching.